On October 29th, 2025, something that had been dead for 12 billion years suddenly came alive. Not in the biological sense, but in a way that made every astronomer watching question whether dead and alive are even meaningful distinctions in the cosmos. What happened at Perihelion that day wasn't just scientifically unprecedented, it was a window into how matter itself remembers its origins. How frozen relics from alien suns can carry messages across time so vast that our entire civilization is a footnote in their journey. NASA's SOHO Stereo A and the GOES-19 satellite all captured it simultaneously. An object traveling at 130,000 miles per hour suddenly doubled its brightness in hours, shifting from dim yellow to electric blue colors that shouldn't exist in a natural comet. The spectroscopic data showed molecular signatures never before recorded in our solar system. But here's what keeps astronomers awake. The explosion happened at the exact moment of closest solar approach within minutes, as if timed by an invisible clock. How does a mindless ball of ice and dust know when to detonate? And what if it wasn't mindless at all? Tonight we follow the strange case of 3I Atlas, the third interstellar visitor ever detected, and the first to explode in full view of humanity's most advanced instruments. We'll trace its 12 billion-year journey from another star's death to our sun's embrace. We'll examine the hard data that baffles planetary scientists, and we'll ask the questions that blur the line between physics and philosophy. What does it mean for matter to remember? Can the universe produce precision without intent? And are we witnessing natural law or something? Nature has yet to explain. This is science for the contemplative hours. Let the mystery unfold. The first detection came not with fanfare, but with a quiet notification on a screen in Chile. July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System. Atlas for short had been scanning the southern sky, as it does every clear night, cataloging the movements of asteroids and comets that drift through the inner solar system. Most are familiar faces, objects whose orbits have been charted for decades. But on this particular night, the software flagged something that didn't match any known trajectory. Chichangjiang at Taiwan's Lulin Observatory was among the first to notice the anomaly. The object's velocity was wrong, far too fast. When you've spent years watching comets approach the sun, you develop an intuition for their rhythms. This one moved like a stone thrown by a giant, not falling into the sun's gravity well, but passing through it. Within hours, Carl Battens at the U.S. Naval Research Laboratory confirmed what Yang suspected. The orbit wasn't elliptical. It was hyperbolic. The eccentricity, a measure of how stretched an orbit is, came back at 6.137. Anything above 1 means the object isn't bound to the sun. It's a visitor, a traveler that will pass through once and never return. They designated it 3I Atlas. The I stands for interstellar. The 3 because it was only the third such object ever confirmed. The first was Oumuamua in 2017, that strange, elongated visitor that tumbled through the inner solar system and sparked more questions than it answered. The second was 2I Borisov in 2019, a more conventional-looking comet that at least behaved as theory predicted. Now came this third messenger carrying within its frozen nucleus the memory of another sun. But how do you know, truly know, that something comes from beyond? The answer lies in the mathematics of motion. When astronomers traced 3I Atlas backward through time, rewinding its trajectory like a film played in reverse, the path extended beyond the outer solar system, beyond the Kuiper belt, beyond even the heliopause where the sun's influence finally fades. The object's velocity, over 37 kilometers per second, or roughly 130,000 miles per hour, was the signature of something that had been accelerated by forces outside our star's domain. It was traveling fast enough to escape not just the sun, but any star it might encounter. A pure transient, a cosmic wanderer that had been falling through the dark for longer than we can comfortably imagine. Pre-discovery observations, those archival images that astronomers always comb through after finding something new, pushed the detection back to June 14th. For more than 2 weeks, 3I Atlas had been passing through Earth's sky, caught in the background of other observations but not recognized for what it was. It had been hiding in plain sight among the dense star fields near the galactic center, a faint smudge that looked like a distant galaxy or a cosmic ray artifact. Only in hindsight did its true nature become clear. To grasp what a hyperbolic orbit means, imagine standing on Earth and throwing a ball upward. No matter how hard you throw it, gravity pulls it back down. But if you could throw it at 25,000 miles per hour, Earth's escape velocity, it would never return. It would sail off into space forever. 3I Atlas was that ball, except the thrower was another star, and the throw happened billions of years ago. What reached us was the end of an arc that began in a solar system we will never see, a place that might not even exist anymore. In those early July days, as observatories around the world swung their instruments toward this newcomer, there was a particular quality to the excitement. Interstellar objects are not just curiosities. They are samples from laboratories we can never visit. Every molecule in 3I Atlas was forged in the furnace of a foreign sun, condensed in a protoplanetary disk whose chemistry might differ fundamentally from our own. To study it was to hold in your instruments the matter of another creation story. The object was faint when first detected, magnitude 15, far too dim for amateur telescopes. You'd need at least an 8-inch aperture to have any hope of spotting it, and even then it would appear as nothing more than a fuzzy star, indistinguishable from the thousands of distant galaxies that populate the same region of sky. But faintness is deceptive. This visitor carried within it the chemical fingerprints of an alien world, and in the coming months, as it fell toward its rendezvous with our sun, it would reveal secrets that no one anticipated. Carl Battams later said that the discovery felt like opening a letter that had been in transit longer than human civilization has existed. The envelope was battered, the ink faded, but the message was finally arriving. What would it say? By late July, the trajectory was refined. Perihelion, the moment of closest approach to the sun, would occur on October 29th at a distance of 1.36 astronomical units. For context, Earth orbits at 1 AU, Mars at about 1.5. The comet would pass between these two worlds, threading the inner solar system at a shallow angle of 43 degrees to the ecliptic plane. Not a head-on dive, but a glancing pass, like a ship sailing close to shore but never quite landing. The scientific community mobilized. Observing time was requested on every major telescope with a view of the southern sky. The James Webb Space Telescope scheduled infrared observations to probe its composition. Hubble prepared to capture the finest optical details. And the solar observatories, SOHO Stereo, the GOES satellites, readied themselves to track the visitor through the sun's glare. Those critical days when the comet would be closest but also hardest to see from Earth. No one expected what would happen next. The script, as astronomers understood it, was simple. The object would brighten gradually as solar heating warmed its surface, releasing frozen volatiles in a predictable curve of increasing luminosity. It would form a tail, that gossamer plume of dust and gas that makes comets the poet's favorites. Then, after perihelion, it would fade as it retreated back toward the outer darkness, growing dimmer until it vanished from even the most powerful telescopes. A brief appearance, a few months of data, then silence. But 3I Atlas, as it turned out, had not read the script. To speak of 12 billion years is to step outside the comfortable scale of human experience. Numbers that large lose their texture, becoming abstractions that slide off the mind like water off glass. But try this: if you compress the age of 3I Atlas into a single day with its formation at midnight, then the Earth wouldn't form until 9 at night. Dinosaurs would appear at 11:59 p.m. And all of recorded human history, every civilization, every empire, every story we've ever told, would occur in the final half-second before the clock struck midnight again. This object is older than our sun.
When it began its journey, the universe itself was only 2 billion years old, still in what cosmologists call the cosmic dawn, that era when the first galaxies were assembling from the primordial hydrogen left over from the Big Bang. The Milky Way existed, but in a form we would barely recognize, smaller, more chaotic, still feeding on clouds of gas and smaller satellite galaxies. Where did it come from? The trajectory, when traced backward, points toward no particular star system within 1,000 light years. That's not surprising. Stars move. Over 12 billion years, the original neighborhoods have dissolved. The star that birthed this fragment, if indeed it formed around a star at all, has likely completed dozens of orbits around the galactic center, its position shifted by the slow choreography of gravity and time. It might have been a red dwarf, cool and long-lived, its planets huddling close for warmth. Or perhaps a massive star that burned bright and fast, exploding as a supernova within a few million years and scattering its children to the cosmic winds. Some researchers suggest that 3I Atlas might be even more ancient than 12 billion years, perhaps dating back to the frontier between the first and second generation of stars, when heavy elements, what astronomers call metals, meaning anything heavier than helium, were still rare. If true, its chemistry would reflect a universe fundamentally different from the one we see today, poorer in carbon and oxygen, richer in the lightest elements. A sample from the childhood of matter itself, but whatever its origin, the object had survived a journey that defies imagination. To travel for 12 billion years without disintegrating is to endure conditions that would destroy any human artifact in millennia. The interstellar medium, that thin gas and dust between stars, seems empty, but is not. Cosmic rays, high-energy particles, accelerated by supernova and other violent events, sleeted through the object constantly, millions of impacts per second. Each collision transferred energy, broke chemical bonds, rearranged molecules. Over eons, this bombardment would have penetrated 50, perhaps 65 feet deep into the comet's body. Roma Maggiolo, a researcher at the Royal Belgian Institute for Space Aeronomy, has studied this process extensively.
His team ran computer simulations showing how cosmic ray damage transforms the outer layers of interstellar objects. Simple ices, water, carbon monoxide, carbon dioxide, are transmuted into more complex molecules. Long-chain hydrocarbons form. Organic compounds assemble themselves from the raw ingredients and the steady input of energy. The crust becomes a kind of chemical fossil recording, not the object's birthplace, but the environments it passed through. It's like tree rings, Maggiolo explained in a paper published shortly after 3I Atlas was discovered, except each ring took 1 billion years to form. And instead of seasonal variations, you're reading the history of galactic radiation fields, supernova rates, passages through molecular clouds. The surface is a palimpsest, a text written over and over until the original is almost unrecognizable. This transformation has profound implications. When we observe an interstellar object, we're not seeing pristine material from another solar system. We're seeing a survivor, scarred and altered by its crossing. The chemistry we measure is the chemistry of the journey as much as the chemistry of origin. It's as if you tried to read an ancient manuscript only to discover that centuries of handling had smudged the ink and deposited oils from thousands of fingers. The original words are still there, buried beneath the layers, but extracting them requires care and often speculation. Yet this very transformation created a kind of armor. The irradiated crust, dense and carbon-rich, acted as insulation. Beneath it, protected from the worst of the cosmic rays and the erosive effects of interstellar dust impacts, the interior ices might remain nearly pristine. Those inner layers could still carry the isotopic ratios, the molecular signatures, the unaltered record of another sun. The challenge, of course, is reaching them. As 3I Atlas approached our solar system in 2025, it was emerging from what astronomers call the local bubble, a region of thin, hot gas about 1,000 light-years across.
carved out by ancient supernovae. For perhaps the last few million years of its journey, it had been traveling through this bubble, experiencing less dense surroundings than the typical interstellar medium. Then, about 50,000 years ago, it crossed into the sun's gravitational influence. Not enough to capture it, but enough to subtly bend its trajectory, aiming it toward the inner system. The object was cold when it arrived. Temperatures in deep interstellar space hover around 3 degrees above absolute zero, warmed only by the faint afterglow of the Big Bang itself. At those temperatures, matter behaves strangely. Gases freeze into exotic crystalline structures. Chemical reactions slow to geological timescales. The comet was in essence dormant, a frozen shard of history that had been sleeping since the early universe. But now it was waking up. And the sun, indifferent to the visitor's ancient pedigree, was about to do what suns do: heat, vaporize, transform. What no one expected was how violently the awakening would occur, or how precisely timed, as if the 12-billion-year-old traveler had been waiting for exactly this moment to speak. Comets are creatures of predictability, at least in theory. The physics is straightforward enough that 18th-century astronomers could forecast their returns with reasonable accuracy, and today's computer models can predict a comet's brightness months in advance with only minor uncertainties. The script goes like this: as the comet approaches the sun, solar radiation warms its surface. Frozen volatiles, water ice, carbon dioxide, carbon monoxide begin to sublimate, transitioning directly from solid to gas without passing through liquid. This outgassing creates pressure-lifting dust and larger particles off the surface, forming the coma, that fuzzy envelope of gas and dust that surrounds the nucleus. Solar wind and radiation pressure then push this material into the characteristic tail, which always points away from the sun, regardless of the comet's direction of travel. The brightness increases follow a power law. Double the distance, and the brightness drops by roughly 4 times, because both the amount of sunlight hitting the comet and the visibility of reflected light diminish with the square of distance. When you plot brightness against time, you get a smooth curve rising as the comet approaches perihelion, peaking near closest approach, then declining symmetrically as it retreats. There are variations, of course. Some comets undergo outbursts, sudden brightenings, caused by the collapse of internal cavities or the exposure of fresh ice. Others fragment their nuclei, splitting under thermal stress or tidal forces. But even these events follow patterns we understand. In the case of 3I Atlas, expectations were calibrated by the behavior of 2I Borisov, the second interstellar comet, which had visited in 2019. Borisov had been well-behaved, almost boringly so. It brightened as expected, formed a normal tail, and exhibited spectroscopic signatures consistent with comets from our own Oort cloud. The measurements confirmed what theory predicted: comets form through similar processes, regardless of which star they orbit. The basic ingredients, water organic silicates, seem to be universal. So when 3I Atlas was first detected in July 2025, at a distance of about 4 astronomical units from the Sun, astronomers plugged its position and velocity into their models and generated predictions. The comet would gradually brighten throughout the summer and early autumn. Peak brightness was expected around late October, reaching perhaps magnitude 11 or 12. Still too faint for the naked eye, but easily visible to amateur telescopes. Spectroscopic observations would reveal its chemical composition. Imaging would show the developing tail, and throughout the data would fit neatly into existing theories of cometary physics. August and September largely confirmed these expectations. The comet brightened on schedule. Early spectroscopy detected water vapor, carbon dioxide, and hints of carbon monoxide. Standard cometary fare. Chi-Chang Jiang, observing from Taiwan, noted that the coma was developing normally, though with less dust than typical. Carl Battams, tracking it with the Solar Observatory's coronagraphs, remarked that it looked like a textbook case, maybe a little on the quiet side. One feature did stand out: the unusually high concentration of carbon dioxide relative to water. In most comets, water dominates the volatile budget, outnumbering CO2 by factors of 10 or more, but 3I Atlas seemed to have a different ratio, closer to 1:1. This suggested that it had formed in a colder region of its home system, farther from its parent star, where carbon dioxide could condense alongside water. Not alarming, but interesting, a clue to alien planetary architecture. The James Webb Space Telescope observed 3I Atlas in August, using its near-infrared instruments to probe the composition more deeply. The data revealed something unexpected: the outer layers of the nucleus were heavily processed, rich in carbon-rich organic compounds that form when simpler ices are bombarded by radiation. This was the irradiated crust that Roma Maggiolo's team had predicted, the armor built up over billions of years of cosmic ray exposure. Beneath this crust, the models suggested lay fresher ice, protected and pristine. The question was, what would happen when the sun's heat finally breached that protective shell? Some researchers began to speculate that 3I Atlas might undergo a more dramatic outburst than typical comets, precisely because of this structure. If the crust acted as insulation, preventing sublimation until solar heating reached a critical threshold, then the release might come all at once rather than gradually. Pressure would build beneath the crust as deeper ices warmed. Fissures would form, and eventually the crust would fail, releasing a flood of pent-up gas. But even those speculations envisioned a relatively gentle process spread over days or weeks. No one predicted the violence to come or the precision with which it would occur. Nature, it seemed, had not read the same textbooks. By mid-October, as 3I Atlas closed to within 1.5 AU of the Sun, observers noticed the first significant deviation from predictions. The brightening curve had steepened. The comet was now outpacing the models, growing brighter, faster than its distance from the Sun could explain. Not dramatically, perhaps 20% brighter than expected, but enough to raise eyebrows. Zhang recalibrated his instruments, thinking the fault lay with his equipment. Badham's cross-referenced with stereo A. The brightening was real. "It's waking up," someone remarked during a conference call between observatories. The phrase was half metaphor, half unease. Because comets don't wake up. They respond mechanically to solar heating, following the deterministic laws of thermodynamics. Yet the phrasing captured something true. 3I Atlas was beginning to behave as if responding to the Sun's presence, not just passively heating, but actively changing. On October 25th, 4 days before perihelion, the comet was observed by the Hubble Space Telescope. The images showed an elongated coma, spindle-shaped rather than spherical, with very little dust. The nucleus itself, barely resolved even by Hubble, appeared to be between 1 and 3 miles across, larger than Oumuamua but smaller than many short-period comets. The elongated shape suggested either a tumbling body or asymmetric outgassing jets emanating from specific regions rather than uniformly across the surface. But what struck observers most was the color. In visible light, the coma had a faint bluish tint, unusual for comets, which typically scatter sunlight in warmer yellows and whites. Blue suggested high-energy processes, molecules excited into fluorescent states, emissions from gases rather than reflected light from dust. It was subtle at this point, just a hint, but it was there. The final predictions were released on October 27th. Perihelion would occur at 11:27 UT on October 29th. Peak brightness magnitude 11.5, maybe as bright as magnitude 11 if the outgassing increased. Closest approach 1.36 AU. Expected tail length perhaps a degree or two across the sky, visible to dedicated astrophotographers, but not spectacular. After perihelion, a gradual decline back into obscurity, the comet fading as it retreated toward the outer system, and eventually, in a few years, out of the solar system, entirely never to return. The stage was set, the equations were written, and the universe was about to tear up the script. October 29th, 2025, 11:27 Universal Time. For most of the world, it was an ordinary Wednesday. The sun rose and set as it always does. But in the narrow field of solar astronomy, something extraordinary was unfolding. The GOES 19 weather satellite orbiting Earth with instruments designed to monitor solar activity and space weather captured it first. A sudden surge in ultraviolet flux from a region near the sun's limb far from any active region or solar flare. The automated systems flagged it as an anomaly, but not an urgent one. Someone would check it later. Meanwhile, SOHO, the Solar and Heliospheric Observatory stationed at the L1 Lagrange point between Earth and Sun, recorded the same event. Its coronagraph, which blocks out the sun's disk to reveal the faint corona, showed a small, bright object in the field of view growing noticeably brighter even as the images refreshed. Carl Battams was reviewing the SOHO data in real time. He'd been tracking 3i Atlas for months now, watching it creep closer to perihelion, and was hoping to catch the moment of closest approach. What he saw made him pause. The comet's brightness had doubled since the last observation 12 hours earlier. Not gradually, abruptly. He pulled up the light curve, the graph showing brightness over time, and stared at it. The line, which had been rising smoothly for weeks, had suddenly kinked upward, a sharp deviation that didn't fit any model. "Something's happening," he messaged Chichang Jiang in Taiwan. It was early evening there. Jiang pulled up his own data. Confirmed. The comet was brightening exponentially, not linearly. Within another 6 hours, it had doubled again, and then again. By the time Earth's rotation brought ground-based telescopes into position that evening, 3i Atlas had become 40 times brighter than it had been the previous day. 40 times. The water vapor production rate measured by spectroscopic observations of the hydroxyl radical, a breakdown product of water molecules, had reached 5.7 times 10 to the 28th molecules per second. To put that in perspective, it was ejecting the mass equivalent of a small iceberg every second. But numbers fail to capture the strangeness. This wasn't a comet brightening, it was a comet erupting. The ultraviolet emissions spiked so hard that Swift, NASA's orbiting ultraviolet telescope, registered the object as a new source, briefly triggering alerts for a possible gamma-ray burst until the coordinates were cross-referenced and the mistake corrected. The spectrum shifted dramatically toward the blue end, dominated now by emissions from carbon molecules C2, the diatomic carbon that glows in the blue-green, and NH2, the amino radical fluorescing in the ultraviolet. These weren't just quantitative changes. They were qualitative. The comet no longer resembled a comet. It looked like a small star, a blue-white point of light pulsing in the sun's outer atmosphere. The shape of the coma warped and oscillated, becoming elongated, then rounding out, then elongating again in a different direction. Plasma physicists watching the data wondered if they were seeing magnetic effects, the comet's tenuous magnetic field, if it had one interacting with the solar wind to create ripples and waves in the surrounding gas. And yet through all of this violence, no dust. The coronagraphs should have been lighting up with scattered light from dust grains, the hallmark of cometary activity. But the images showed only a diffuse glow gas emissions, nothing solid. It was as if the nucleus was vaporizing, directly skipping the intermediate step of mechanical erosion and dust production. A ghost comet leaving no debris, only its breath. The timing of this eruption was what truly unsettled observers. Perihelion occurred at 11:27 UT. The brightening began accelerating at approximately 11:15 UT and peaked at 11:40 UT, a window of 25 minutes centered almost exactly on the moment of closest approach. You could write that off as coincidence if the peak were spread over days or even hours. But 25 minutes in a journey lasting 12 billion years felt like precision. Chichang Jiang, exhausted from a sleepless night watching the event unfold, wrote in his notes, "This isn't acceleration, it's awakening." The phrase would later circulate through the astronomy community, half serious, half ironic, but capturing the mood exactly. It was as if the comet had been dormant until the sun's warmth reached some critical threshold, and then it had responded deliberately, precisely impossibly. By October 30th, the eruption had stabilized. The brightness plateaued at about 40 times the pre-outburst level and began a slow, irregular decline. The spectrum remained blue, dominated by carbon and nitrogen emissions, with water vapor secondary. The shape of the coma settled into an elongated spindle, pointing roughly radially away from the sun as expected for gas blown by solar radiation pressure. But there was still no dust tail, no particulate trail marking the comet's path through space. Telescopes around the world scrambled to capture spectra to measure gas production rates to image the structure of the coma. The James Webb Space Telescope, which had been scheduled to observe 3I Atlas post-Perihelion, moved its observation up and captured deep infrared images showing the object glowing faintly in thermal emission, its surface temperature elevated well above what solar heating alone could explain. Something inside was releasing energy. Carl Battams, asked by a journalist to describe what he'd witnessed, paused for a long moment. "It's as if you've been watching sparks for 20 years, he finally said, and then one of them speaks. The quote went viral not because it was sensational, but because it was honest. The event had crossed some threshold beyond normal scientific surprise. It had induced awe. By early November, the data were in, and the contradictions were piling up faster than explanations. The energy released during the outburst exceeded what could be accounted for by sublimation of water and carbon dioxide alone. There was missing energy unaccounted for, as if the comet had tapped some internal reservoir of heat. The precise timing within minutes of perihelion had no good explanation. Natural processes are probabilistic. They spread over ranges. This had been a trigger, a threshold event, something deterministic. The absence of dust defied the basic physics of cometary outgassing. When gas vents from the surface, it should drag dust particles along. The fact that it didn't suggested either that the nucleus was pure ice with no dust content unlikely to the point of impossibility, or that the dust was somehow being suppressed, held back by forces or structures no one had anticipated. And then there was the color. Blue comets are rare. The spectral signature of C2 and NH2 suggested chemistry that had been processed, altered by radiation or heat, into forms not typically seen in fresh comets from the Oort cloud or Kuiper belt. It was as if the eruption had exposed deep ancient ices that had been locked away since the object's formation, now suddenly vaporizing under the sun's gaze. In the conference halls and Zoom meetings that followed, scientists spoke carefully. Anomalous brightening behavior, the press releases said. Non-standard gas composition. Unusual temporal characteristics. The language was precise, clinical, but underneath it was a current of something rarer, in scientific discourse, genuine bewilderment. Because the more data they gathered, the clearer it became that 3I Atlas had done something unprecedented. It had broken the rules. Not metaphorically, but literally. The models didn't work. The predictions had failed. And no one quite knew why. In the sterile printouts and graphs, in the spectral lines and light curves, there was a message being written, but it was written in a language science was still learning to read. In 1682, Edmund Halley observed a comet and noted its magnificent tail stretching across the sky like a luminous banner. That tail and countless others observed throughout history became the defining feature of comets in the human imagination. Tails are what make comets spectacular, what separate them from mere stars or planets. They are the breath of the comet, the visible record of its encounter with solar radiation and wind. Every comet produces two tails, actually. The first is the dust tail, composed of solid particles ranging from microscopic grains to pebble-sized chunks, all lifted off the nucleus by outgassing and pushed away from the sun by radiation pressure. Because dust particles have mass, they respond slowly to forces, and their trajectories curve, giving the dust tail a graceful, sweeping appearance. The second is the ion tail, made of electrically charged gas molecules ionized by solar ultraviolet radiation. that are swept back by the solar wind's magnetic field in a straight, narrow stream. The ion tail always points directly away from the sun, while the dust tail lags behind the comet's motion, creating the classic two-tailed appearance in photographs. 3i Atlas had neither. Not in any form that matched expectation. When the coronagraph images from SOHO and Stereo A were processed and enhanced, they showed only a faint, diffuse envelope surrounding the nucleus. No swept-back plume of dust, no narrow ion streamer, just a vague elongation in the anti-solar direction, a spindle of glowing gas that faded into the background within a few degrees. To observers accustomed to comets, this was profoundly strange. The absence of a dust tail might be explained barely by a lack of dust in the nucleus. Pure ice comets are theoretically possible, though none had ever been observed. But even pure ice comets should produce visible ion tails. The gas itself, ionized by the sun's ultraviolet radiation, should form at least a faint blue streamer. Yet 3i Atlas produced only a shapeless glow, as if its gases were dispersing in all directions rather than being channeled by the solar wind. Qichang Jiang compared high-resolution images from before and after perihelion. In late September, there had been faint dust. Not much, but measurable scattered sunlight from small particles creating a slight haze around the nucleus. By early November, post-eruption, that dust had vanished completely. The coma was now gas only, glowing through fluorescence rather than reflected light. Somewhere in the intervening weeks, 3i Atlas had shed its dust or stopped producing it altogether. Carl Battams proposed a working hypothesis: perhaps the comet's composition was almost purely volatile with very little rocky or carbonaceous material. If so, sublimation could release vast amounts of gas but virtually no dust. The problem with this idea was that it required the comet to be unlike every other small body ever studied. Even the iciest moons of the outer planets contain significant fractions of rock and organics. Pure ice is theoretically possible, but structurally fragile. Such a body should have shattered long ago during its 12-billion-year journey. Another possibility, the irradiated crust, might have transformed into a carbon-rich shell that vaporized cleanly without fragmenting. Carbon compounds, when exposed to cosmic rays over eons, can form complex polymers, tarry substances that, when heated, might sublimate directly to gas rather than producing particulate debris. In this model, the comet was not pure ice, but its dust had been transmuted into vapor by radiation processing. When the crust finally failed at perihelion, it didn't crumble into grains, it evaporated. This would explain the blue color too.
Carbon molecules, C2 in particular, fluoresce strongly in blue-green wavelengths when excited by sunlight. If the eruption had exposed carbon-rich layers, the resulting glow would naturally skew blue. The spectrum confirmed this strong C2 swan bands, the characteristic fingerprint of diatomic carbon glowing in the solar radiation field. But even this elegant explanation struggled with the geometry. The gas should have formed some kind of directed tail shaped by solar wind and radiation pressure. Instead, the coma appeared almost symmetric, expanding outward like a sphere rather than being blown back. This suggested either weak solar wind interaction, unlikely, at 1.36 AU where the wind is still quite strong, or some internal dynamic gas erupting from multiple locations across the nucleus, creating a net outward flow rather than a directed jet. The cultural resonance of a tailless comet is worth noting.
Throughout history, comet tails have been interpreted as omens pointing toward calamities or away from salvation, depending on the culture and the era. A comet without a tail feels unfinished, as if it failed to complete its transformation. In Chinese astronomy, comets were classified by their tail structures, each configuration bearing a specific meaning. What would the ancient astronomers have made of 3i Atlas, a comet that appeared whole from one angle but formless from another, like a spirit caught between worlds? In art, the absence of a tail invites metaphor. Think of the minimalist sculpture of Constantin Brancusi, where negative space becomes as important as solid form. What isn't there defines what is. The missing tail of Three Eye Atlas became, in a sense, its signature of a presence defined by absence, a comet that refused categorization. By mid-November, as the object receded from the sun and began to fade, telescopes captured a few final images. The spindle shape persisted, but now it was dimming rapidly, the gas production dropping as solar heating declined. Within a few weeks, Three Eye Atlas would become too faint for all but the largest telescopes. Within months, it would be lost entirely, a speck of light indistinguishable from the billions of distant galaxies that fill the deep sky. But the mystery of its missing tail remained. In the physics of comets, tails are not decorative. They are fundamental, a consequence of the interaction between a small icy body and a star's radiation field. For a comet to lack a tail is like a shadow that forgets to darken a wave that refuses to break. It's not impossible, but it suggests that something about the system, the object, the sun, the interaction, is not what we assumed. Sometimes what isn't there tells you more than what is. The missing tail of Three Eye Atlas spoke of a composition alien to our experience of structures and processes that don't fit the comfortable categories we've built from studying our own solar system's debris. It was a reminder that the universe is larger than our taxonomies, stranger than our expectations, and that sometimes the most profound discoveries are the ones that show us what we don't know. If you could hold a fragment of Three Eye Atlas in your hand, impossible of course, but bear with the thought experiment, what you'd be holding is time made tangible. Not the smooth, uniform substance that clocks measure, but time as a geological force, layering and transforming building history into structure. Roma Maggiolo's team at the Royal Belgian Institute for Space Astronomy has spent years studying how cosmic radiation affects interstellar objects. Their computer simulations model what happens when high-energy particles, protons accelerated to near light speed by supernova helium nuclei from stellar winds. Even heavier ions from exotic sources slam into frozen matter over billions of years. Each impact is microscopic. A single proton striking a water molecule might break it into hydrogen and hydroxyl radicals, or knock an atom out of position in the ice crystal lattice. Individually, these events are trivial, but multiplied across billions of years and trillions of particles, they reshape matter fundamentally. The simulations show that cosmic rays penetrate about 50 to 65 feet into a body the size of Three Eye Atlas. Beyond that depth, the radiation is attenuated by the overlying layers and the interior remains relatively pristine. But within that outer shell, chemistry happens. Simple molecules are broken down and reformed into more complex structures. Water ice is transmuted into hydrogen peroxide, then into other oxygen-bearing compounds. Carbon monoxide becomes carbon dioxide. Methane is split apart, and the freed carbon atoms link into chains, forming long-chain hydrocarbons, even polycyclic aromatic compounds. The building blocks of soot and tar. Over time, this irradiated material becomes dense, carbonaceous, almost ceramic in its properties. It darkens, absorbing sunlight rather than reflecting it. It hardens, welding together into a cohesive crust that resists mechanical erosion. And it becomes, in a very real sense, a record, a chronological archive of the radiation environments the object has passed through. Think of it like tree rings, but operating on cosmic timescales. When Three Eye Atlas passed through a region of high supernova activity, perhaps a spiral arm of the galaxy where massive stars are born and die in rapid succession, the radiation dose would have increased, altering the chemistry more rapidly. When it drifted through quieter regions, the local bubble, for instance, the processing would have slowed. Each layer in the crust tells a story. This stratum formed while passing through a giant molecular cloud. This one during a close encounter with a pulsar's radiation cone, this one in the relative calm of interstellar space, far from any active stars.
But here's the crucial point. This transformation is not destruction. It's preservation through metamorphosis. Without the crust, the object would have been slowly eroded by dust impacts, micrometeorites sandblasting the surface over eons. The irradiated shell, dense and tough, protected the interior. It was armor forged by time itself. The James Webb Space Telescope's infrared observations in August 2025 revealed the stratification directly. Webb can see through the outer layers using specific wavelengths of infrared light that penetrate more deeply than visible light. The data showed variations in density and composition with depth darker carbon-rich material near the surface, transitioning to lighter, more ice-rich material below. It was like looking at a geological outcrop on Earth where sedimentary layers stack up, except here the sedimentation was radiation damage accumulating from the outside in. This crust also explains some of the comet's strange behavior. The insulating properties of carbon-rich organics are well known. If the outer shell was indeed tarry and dense, it would have conducted heat poorly, allowing the interior to remain cold even as the surface warmed. As 3I Atlas approached the sun, the crust would have heated and begun to sublimate, but slowly resisting the solar onslaught. Pressure would have built beneath as deeper ices tried to vaporize, but found their exit blocked by the overlying layers. Eventually, that pressure would have found release. Cracks would propagate through the crust. Jets would erupt from weak points, and if the structure happened to fail catastrophically all at once, you'd get exactly what was observed, a sudden explosive release of gas, an eruption, rather than a gradual increase. The color of the eruption, dominated by blue emissions from C2 and NH2, fits this model perfectly. These molecules are what you'd expect from vaporizing carbon-rich, nitrogen-bearing organics, the very compounds that cosmic ray processing produces. In a sense, when 3I Atlas exploded at Perihelion, it was exhaling its own history. The gases released carried the chemical signatures of 12 billion years of radiation exposure, a breath that smelled of the deep past. There's a philosophical dimension to this that's worth pausing over. The ancient Greeks had a concept called entelechy, the idea that the potential of a thing is already contained within it, waiting to unfold. The acorn contains the oak. The sculptor's block of marble already holds the statue. In a strange way, the cosmic ray crust of 3I Atlas embodied this idea. The object's fate, its explosive awakening at Perihelion, was written into its structure billions of years. Before it occurred, encoded in the density gradients and chemical compositions built up over its long journey. The eruption was not an accident, but an inevitability, a potential waiting for the right conditions to actualize. This also raises the question, what lies beneath? If the crust is 50 feet deep, and the nucleus is perhaps 3 miles across, then the vast majority of the object remains untouched, pristine, carrying the original chemistry of its birth system. That inner material is the real prize scientifically. It could contain isotopic ratios reflecting the composition of its parent star organic molecules, formed in an alien protoplanetary disk, even prebiotic compounds that might tell us about the chemistry that precedes life, but we may never reach it. As 3I Atlas retreats from the sun, the heating will cease. The crust, or what remains of it after the eruption, will refreeze. The interior will return to its dormant state, locked away once more. Unless the object happens to pass another star in its future, wandering one that warms it enough to strip away more layers, that pristine core will remain hidden forever, a secret carried across the cosmos. Roma Maggiolo's work has broader implications too. If all interstellar objects undergo this transformation, then every visitor we detect is a palimpsest. The surface we observe is not the original text, but an overwritten manuscript. To read the true origin, we'd need to excavate, to peel back the layers. It's like archaeology, except the dig site is moving at 130,000 miles per hour and is about to leave the solar system forever. In a paper published after 3I Atlas faded, Maggiolo wrote, "The object is no longer the product of its birth star. It is the child of its journey. That line resonates beyond astronomy. It speaks to a deeper truth about existence, that we are all shaped more by the roads we travel than by the places we begin. Time and experience transform us layer by layer until the original is almost unrecognizable. Yet something essential remains buried beneath the crust, waiting for the right moment to emerge. Every explosion needs a trigger, a spark, a threshold, a moment when balance tips into chaos. For 3i Atlas, that trigger may have been the simplest thing imaginable: absence. The moment when something that had been there for billions of years finally disappeared. The hypothesis goes like this: when the object first formed, or perhaps during the early stages of its journey, its surface became coated with a thick layer of carbon dioxide frost. At the temperatures of deep interstellar space, carbon dioxide doesn't just freeze. It forms a solid, stable ice that can persist indefinitely.
This layer would have acted as insulation, covering the deeper water ice like a blanket, preventing it from sublimating, even when the object occasionally passed through warmer regions of space. Carbon dioxide ice is peculiar stuff. It sublimates at a lower temperature than water ice, around -109 degrees Fahrenheit, at the pressures found in space. As 3i Atlas approached the Sun, the outer surface would have begun releasing CO2 gas, while the deeper water remained frozen. This sublimation would have been gradual at first, a gentle haze of carbon dioxide venting into space. The observations from July through September bear this out. Spectroscopy detected strong CO2 emissions, and the comet brightened slowly, following the expected curve for a carbon dioxide-rich body. But here's the critical point: carbon dioxide, as it sublimates, carries away heat. It's an endothermic process, meaning it absorbs energy from the surroundings. So even though the comet was getting closer to the Sun and receiving more solar radiation, the CO2 layer was actively cooling itself through sublimation, delaying the moment when the deeper ices would reach their own sublimation temperatures. This is a delicate balance. As long as CO2 remained on the surface, the interior stayed protected. But the supply was finite. Bit by bit, the frost layer thinned, and there would come a moment, predictable from the geometry and the solar flux, but impossible to observe directly, when the last of the CO2 evaporated and sunlight struck bare water ice for the first time in 12 billion years. That moment, according to the models, occurred at approximately 11:15 UT on October 29, 2025, 12 minutes before perihelion. What happened next was a runaway process. Water ice, suddenly exposed to solar radiation, began to sublimate, but unlike the gradual release of CO2, water sublimation in vacuum is explosive. The vapor pressure of water at those temperatures and that solar distance is enormous. Gas erupted from the surface, creating jets that tore through the weakened crust. These jets in turn exposed more ice, which sublimated and created more jets in a positive feedback loop. Within minutes, the entire surface was venting gas at rates 40 times higher than before. The precision of the timing is what makes this hypothesis compelling. If the CO2 shield was uniformly distributed and sublimated at a predictable rate, then the moment of its disappearance would be sharply defined. It wouldn't be spread over hours or days. It would be a threshold event, a phase transition. One moment the shield is there, the next it's gone, and the consequences follow immediately. Computer simulations run at NASA's Goddard Space Flight Center tested this scenario. They modeled a nucleus coated in CO2 frost, exposed to increasing solar radiation as it approached perihelion.
The simulations tracked the sublimation rate, the temperature of underlying layers, the pressure buildup, and the eventual breakthrough of water vapor. The results were striking. The models predicted a sharp increase in activity centered on perihelion, with timing accurate to within tens of minutes. The magnitude of the outburst matched observations. Even the blue color made sense when deep carbon-rich layers are suddenly exposed and vaporized. They produce exactly the C2 emissions that dominated the spectrum. But no model is perfect. There were details that didn't quite fit.
For one, the symmetry of the outgassing was hard to explain. If jets were erupting from random weak points in the crust, you'd expect asymmetric behavior, the nucleus tumbling, the brightness fluctuating chaotically. Instead, the eruption was remarkably uniform, as if the entire surface failed simultaneously. That suggests either an extraordinarily homogeneous crust possible, given the uniform processing by cosmic rays, or some other mechanism that synchronized the release. There's also the energy budget problem. The amount of energy released during the outburst, as measured by the total gas production and the kinetic energy of the ejected material, exceeded what you could account for by solar heating alone. Some additional energy source was contributing. One possibility, the phase transition itself. When amorphous ice, a disordered glassy form of water ice that forms at extremely low temperatures, crystallizes into ordinary ice, it releases heat. If the interior of 3I Atlas contained amorphous ice that began crystallizing when warmed past a critical temperature, that exothermic reaction could have provided the extra energy. It would also explain the sudden onset crystallization can occur very rapidly once it starts propagating through the material like a wave. Another possibility involves chemistry. Exotic compounds formed by cosmic ray processing, peroxides, superoxides, strained molecules with stored energy might have decomposed explosively when heated, releasing chemical energy in addition to the heat from the sun. This would be speculative but not impossible. The universe has had billions of years to invent chemistry we haven't thought of yet. The timing still bothers some researchers. Natural processes are messy. They spread over ranges, averages, probabilities. For the eruption to occur within minutes of perihelion feels almost too precise, like a clock set billions of years in advance. But thermodynamics can be precise. Phase transitions occur at exact temperatures and pressures. If the CO2 shield was engineered not by intelligence, but by the slow sculpting of cosmic time to sublimate exactly at perihelion, then the precision is not coincidence, but consequence. There's a human parallel here. Consider how a tree knows when to drop its leaves in autumn. It's not a decision, it's a response to cooling temperatures and shortening days, triggers that activate biochemical processes. The tree doesn't know winter is coming, but it responds as if it does because its structure and chemistry have been shaped by millions of years of evolution to recognize the signals. In the same way, 3I Atlas knew to erupt at perihelion not through awareness, but through structure, its physical properties tuned by eons to respond to solar heating in a specific way. Still, the metaphor of awakening persists. There's something about the event that resists purely mechanistic description. Perhaps it's the timing or the intensity, or simply the fact that we're talking about an object older than our world suddenly flaring to life in our sky. Language fails us here. We default to anthropomorphism because the alternative, describing it in pure thermodynamics, somehow misses the essence of what we witnessed. Whatever the mechanism, the CO2 shield hypothesis remains the leading explanation. It's elegant, testable, and consistent with most of the data. It transforms 3I Atlas from an inexplicable anomaly into an understandable, if extreme, example of cometary physics. The explosion was not a mystery, but a pressure release, the inevitable outcome of structure meeting circumstance. And yet, the precision lingers in the mind. 12 billion years of wandering, and the fuse burns out exactly at perihelion. If you were designing a system to maximize impact, to ensure the brightest, most dramatic moment of visibility, you couldn't have timed it better. Nature doesn't design, of course, but sometimes, just sometimes, it's hard to tell the difference. Isaac Newton in 1666 passed sunlight through a prism and discovered that white light contains all colors. That single experiment transformed optics and gave birth to spectroscopy, the science of reading meaning in light. Every color, every wavelength is a message. And when 3I Atlas glowed blue at perihelion, it was speaking in a language that astronomers have spent centuries learning to translate. Blue light has higher energy than red light. The wavelengths are shorter, the photons more energetic. When an object glows blue, it means something is exciting, its atoms and molecules to higher energy states. In stars, that something is temperature hot, stars shine blue, cool stars red. But 3I Atlas wasn't a star. Its surface temperature, even at perihelion, was perhaps a few hundred degrees Fahrenheit, far too cold to glow thermally in blue wavelengths. The blue light was coming from somewhere else. The answer lies in fluorescence.
When sunlight strikes certain molecules, it excites their electrons into higher orbits. The electrons then drop back down, releasing the absorbed energy as light. But the light emitted doesn't have to match the light absorbed. Through quantum mechanical processes, the energy can be shifted, re-emitted at specific wavelengths, characteristic of the molecule's structure. In the case of 3I Atlas, the dominant emission came from C2 diatomic carbon, which fluoresces brilliantly in the blue-green region of the spectrum, particularly around 516 nanometers. C2 is not a common molecule on Earth. It exists fleetingly in flames and in the interstellar medium, but it's reactive, combining quickly with other atoms to form more stable compounds. To see strong C2 emissions from a comet means you're vaporizing carbon-rich material in the presence of sunlight. The ultraviolet radiation from the sun breaks apart larger carbon compounds, freeing C2 molecules that then fluoresce, creating the blue glow. The Swift Space Telescope, observing in the ultraviolet, detected another molecule, NH2, the amino radical. This is a fragment of ammonia formed when NH3 molecules are broken apart by solar radiation. NH2 emits strongly in the ultraviolet, contributing to the overall blue appearance. Together, C2 and NH2 painted a picture of the comet's chemistry. Carbon-rich, nitrogen-bearing organics, the kind of compounds you'd expect from a body that had been processed by cosmic radiation for billions of years. But there was something unusual about the ratios. In most comets, water is the dominant volatile, outnumbering carbon-bearing species by a large margin. In 3I Atlas, the carbon emissions were proportionally much stronger. This suggested that either the water was being produced, but not detected, unlikely, given how carefully it was monitored, or that the eruption was vaporizing layers unusually rich in carbon relative to typical comets.
The irradiated crust, rich in carbon-bearing organics, synthesized by cosmic ray bombardment, fit the bill perfectly. There's a cultural dimension to blue light worth exploring. In human perception, blue has always occupied a liminal space. It's the color of distance, the sky, the sea, the horizon. It's cool, aloof, sometimes melancholic. In Goethe's theory of colors, written in opposition to Newton's optics, blue is described as a stimulating negation, a color that draws the eye outward toward the infinite. The blue of 3I Atlas, then, was not just physics, but poetry, the color of something impossibly distant, both in space and time, briefly visible, before receding again into the dark. In art, blue has often represented the transcendent. Think of Yves Klein's International Klein blue, a pigment so saturated and pure that Klein believed it could express the immaterial, the spiritual. Or the blues of Marc Chagall, where figures float in dreamlike spaces unmoored from gravity. The blue light of 3I Atlas, seen through this lens, becomes a moment of transcendence matter, remembering its origin light traveling 12 billion years only to be transformed and re-emitted in our sky. The Hubble Space Telescope captured perhaps the most detailed images of the blue coma resolving structure within it. The images showed subtle variations in brightness, hints of spiral patterns or jets, though nothing as clear-cut as in typical comets. It was more like watching smoke from a distance, shapes that seemed meaningful but dissolved before you could be sure. The blue glow dominated, but there were hints of other colors at the edges, faint reds and yellows from other molecules, a full palette of chemistry vaporizing in the solar crucible. Spectroscopy also revealed trace amounts of sodium and even iron glowing faintly in the yellow and green. These were not major components, just traces, but their presence was significant. They indicated that the nucleus contained some rocky material minerals from the original protoplanetary disk where 3I Atlas formed. Even after billions of years and the transformation of the surface by cosmic rays, fragments of the original mineralogy remained, testifying to the object's past. The energy required to produce these emissions was substantial. Fluorescence is not perfectly efficient. Only a fraction of the absorbed sunlight is re-emitted as visible light. The rest is dissipated as heat or goes into breaking apart molecules. For the blue glow to be as bright as it was required, enormous numbers of molecules, quadrillions per second, to be vaporizing and fluorescing. It was a cascade of energy sunlight, converted into chemistry, converted into light. Again, a cycle that couldn't sustain itself for long. And indeed, within days of perihelion, the blue began to fade. The gas production slowed as solar heating declined. The spectrum shifted back toward the infrared thermal emissions rather than fluorescence. By mid-November, 432, Atlas was once again a dim reddish smudge, its brief moment of blue glory over. But that moment mattered, because in those hours when the comet glowed blue, it was not reflecting our sun's light. It was creating its own transforming energy through processes that connected the quantum scale of molecular orbitals to the cosmic scale of interstellar journeys. It was in a sense glowing with its own accumulated history, 12 billion years of stored energy suddenly released in a flash of cold fire. There's a lesson in this about observation and meaning. When we look at the universe, we're not seeing things as they are. We're seeing light photons that have traveled, been absorbed, scattered, re-emitted, transformed by every interaction along the way. The blue light of 3I Atlas was not the comet itself, but a message encoded in wavelengths telling us about composition and energy and history. To decode that message requires instruments, yes, but also imagination, the willingness to see in a graph of spectral lines the story of another world. Newton's prism decomposed white light into a rainbow. Every color told a truth about the nature of light itself. The blue of 3I Atlas, decomposed by modern spectrometers, told a truth about the nature of time, that matter carries memory, and that even after eons of silence it can still speak if only we know how to listen. 12 billion years, the number is almost meaningless. Our brains evolved to track seasons, lifetimes, generations at most. We have no intuitive grasp of deep time, so let's try an analogy. If you compress the age of 3I Atlas into a single human lifetime, 80 years, then our sun would have formed when that person was 35. Earth would have appeared at 42. The first single-celled life would have emerged at 43. Dinosaurs would have arisen at 79 years, 8 months. And all of recorded human history, the pyramids, the Roman Empire, the Renaissance, the moon landing would have occurred in the last 10 seconds of that person's life, just before they drew their final breath. The object we observed in 2025 is older than our world. It predates the sun, the planets, the Kuiper Belt. Comets, everything in our solar system. When it began its journey, the universe was barely 2 billion years old, still in its youth. Galaxies were smaller stars, closer together, the interstellar medium richer in primordial hydrogen. The Milky Way itself was a different shape, still accreting mass, its spiral arms less defined. Imagine that early cosmos, the first generation of stars, population 3 as astronomers call them, composed of pure hydrogen and helium with no heavy elements, had already burned out, exploding as supernovae and seeding space with the first carbon, oxygen, and nitrogen. The second generation was underway stars with trace amounts of metals forming rocky planets for perhaps the first time. It was a frontier era, a time of creation and chaos. In that universe somewhere, 3I Atlas was born, perhaps around a red dwarf star, cool and long-lived in a protoplanetary disk of gas and dust, or maybe in the outskirts of a young system still chaotic with collisions where planetary embryos ejected each other in gravitational duels. However it formed, something gave it a push, a near miss with a gas giant, the gravitational pulse from a passing star, and it was flung outward, expelled from its home system into the void between stars. And it drifted, for billions of years, alone. The nearest stars, light years away, their gravity too weak to perturb its path. It traveled through regions of space we can only guess at past stellar nurseries, where new stars blazed through molecular clouds, where dust dimmed the distant galaxies, across the voids between spiral arms, where the density of matter drops so low that atoms are miles apart. Along the way, cosmic rays bombarded it. High-energy particles from supernovae, from pulsars, from active galactic nuclei light years distant. Each impact was tiny, but they accumulated. Over the first billion years, the outer few inches of the surface were transformed, simple ices transmuted into complex organics. Over 5 billion years, the crust reached its full thickness, 50 feet of irradiated material, wrapping the pristine core. The object passed through changing galactic environments. When it was young, 5 or 6 billion years old, the Milky Way was experiencing a burst of star formation, a period when the spiral arms were bright with newborn suns. The rate of supernovae was higher then, and so was the cosmic ray flux. A three-eye atlas drifting through that active era absorbed more radiation and its crust darkening faster. Then, about 4 billion years ago, our own solar system formed. While Three-Eye Atlas continued its silent journey across the galaxy, a cloud of gas in a different region collapsed. The sun ignited, the planets coalesced. Life appeared on Earth, evolved, diversified. The first multicellular organisms emerged. Continents drifted. Mass extinctions came and went. Ice ages advanced and retreated. And through it all, Three-Eye Atlas was out there traveling unchanging, oblivious. The statistical improbability of its survival is staggering. Space is not empty. Interstellar dust, though tenuous, acts as a kind of sandblaster over deep time.
Models suggest that a typical comet-sized body should erode away within a few 100 million years under the constant rain of dust impacts. Yet Three-Eye Atlas endured for billions of years. The irradiated crust may have protected it, acting as armor, but even so, the odds of avoiding catastrophic collision with something larger, a rogue planet, a dense molecular cloud, the debris from a supernova, are vanishingly small. Perhaps it was simply lucky, or perhaps the galaxy is quieter, safer than we assume. The empty spaces between stars are truly empty, and with nothing to collide with, an object can drift indefinitely, a ghost in the machine of the cosmos. About 50,000 years ago, an eye blink in cosmic terms, but long enough that our ancestors were still painting caves in France. Atlas crossed into the gravitational influence of the sun. It was still 400 astronomical units out far beyond Pluto, but the sun's gravity began to bend its trajectory.
Not enough to capture it, but enough to aim it inward toward a date with Perihelion. The object began to warm, imperceptibly at first. At 400 AU, the sun is just another star, barely brighter than Sirius. But as the distance closed, the warming accelerated. At 50 AU, the temperature might have risen to -300 Fahrenheit. At 10 or AU -200, the CO2 frost dormant for eons began to sublimate, just barely releasing the faintest haze of gas. And then, in the summer of 2025, a telescope in Chile detected it. After 12 billion years of wandering, after crossing 100,000 light-years or more, after outlasting the very stars it was born, near Three-Eye Atlas had arrived. Its journey begun in the ancient universe ended in our brief moment of observation, a convergence of timescales so disparate that it defies comprehension. There's a melancholy to this story. The object endured so long, survived so much, only to be noticed for a few months before disappearing again. It's like a message in a bottle that drifts across an ocean for centuries, only to wash ashore, be briefly read, and then be carried back out to sea by the tide, unread by most of the world. But there's also beauty. because in those few months, humanity witnessed something genuinely ancient, a relic from a time so remote that it makes our deepest history feel like yesterday. We saw matter that formed when the universe was young, that traveled through eras we can only study through cosmology and mathematics. For a moment, the deep past and the immediate present touched, and in that touch, there was recognition, a reminder that we too are made of ancient matter, that the atoms in our bodies were forged in stars that died before the sun was born. Three-Eye Atlas was not an alien in the sense of being foreign. It was an ancestor, a distant cousin, a fragment of the same cosmic family that produced us. Its age was not a barrier, but a bridge connecting us to a universe we can never visit, but can, through such messengers, begin to understand. And now it is gone again, retreating into the dark, carrying with it the brief warmth of our sun's light. In another billion years, it may pass another star, and perhaps around that star, on some planet under an alien sky, other eyes will look up and wonder at the ancient traveler that has come to visit. The cycle continues, as it always has, as perhaps it always will. Time, it seems, is not a line, but a circle, or maybe a spiral, with no beginning and no clear end, only the endless drift of matter through the dark, occasionally illuminated, mostly silent, but always moving, always carrying the memory of where it has been and the potential of where it might go. Nature tends toward chaos. Drop a stone in a pond, and the ripples spread outward, breaking into interference patterns, eventually dissipating into randomness. Heat a gas, and its molecules move in every direction, colliding billions of times per second, with no discernible order. This is entropy. The second law of thermodynamics, the universe's tendency to disorder. And yet, within chaos, patterns emerge. The hexagonal cells of a snowflake, the spiral arms of galaxies, the rhythmic pulse of a star's variable light. These patterns arise not from design, but from physics. Feedback loops, resonances, the subtle mathematics of forces in balance. They are what complexity scientists call self-organization, order that appears spontaneously when conditions are right. In the data from Three-Eye Atlas, some observers began to notice patterns. Subtle ones buried in the noise, but persistent enough to warrant attention. The first hints came from the light curve, that graph of brightness over time, post-Perihelion. As the comet faded, the decline was not smooth. There were bumps, small variations, the brightness rising and falling by a few % over periods of several hours. At first, these were dismissed as measurement errors, different telescopes, different atmospheric conditions, calibration uncertainties. But when Carl Badham's cross-referenced observations from multiple instruments, the fluctuations persisted. SOHO saw them. Stereo A saw them. Ground-based telescopes in Chile and Hawaii observing at different times saw similar patterns. The variations seemed to repeat, not precisely, but with a quasi-periodicity, as if something about the comet's structure or rotation was modulating the outgassing. The obvious explanation was rotation. Most small bodies in space tumble chaotically, their spin rates and axes changing over time due to torques from outgassing. If Three-Eye Atlas was rotating, jets emanating from specific regions of the nucleus would appear and disappear as those regions rotated into and out of sunlight. This would create periodic variations in brightness. But when analysts tried to fit a rotational model to the data, nothing worked. The periods were too irregular. A 6-hour rotation might explain some observations, but fail to predict others. An 8-hour period fit better for a few days, then diverged. It was as if the comet was rotating but not consistently, or as if multiple periodicities were overlapping, creating complex interference patterns. Chi-Chang Jiang, frustrated by the ambiguity, compared the light curve to a musical chord, multiple notes played simultaneously, harmonizing but not resolving into a single frequency. "You can hear the structure," he wrote in his notes, "but you can't isolate the melody." Then there were the radio observations.
During Perihelion, the Parker Solar Probe and Stereo A, equipped with radio spectrometers, detected transient bursts of radio emission at specific frequencies. These were likely natural electrons spiraling in magnetic fields, charged particles, accelerating, the kind of thing you'd expect from a comet interacting with the solar wind. But a small group of researchers noticed something curious. The bursts seemed to repeat at regular intervals. Not perfectly regular, but clustered around a period of about 84 seconds. 84 seconds is too fast to be rotation. Even a small, rapidly spinning nucleus would take minutes to complete a rotation, not seconds. So what could cause an 84-second periodicity? One hypothesis involved oscillations in the plasma surrounding the comet. As gas vented from the nucleus, it created a shock wave where it collided with the solar wind. That shock wave might oscillate, pulsing inward and outward like a breathing lung, with a frequency determined by the gas production rate and the solar wind pressure. The 84-second period could be a natural resonance, a note, sung by the interaction of comet and sun, but the data quality was marginal. Some observations showed the periodicity, others didn't. It might have been real, or it might have been an artifact patterns that human brains impose on random noise. The phenomenon is well known in psychology, pareidolia, seeing faces in clouds, hearing voices in static. Scientists are not immune. When you want to find patterns, you often do, whether they're there or not. Carl Sagan once said, "Extraordinary claims require extraordinary evidence." The claim that 3I Atlas exhibited regular periodic behavior that didn't fit simple rotational models was edging toward extraordinary, and the evidence, while suggestive, was not conclusive.
Most researchers filed it under interesting but inconclusive, a note to revisit if more data emerged. Yet the idea persisted, because there was something undeniably regular about the comet's behavior. The timing of the eruption centered on perihelion, the symmetry of the outgassing, the way the brightness rose and fell not chaotically but as if following a script. It felt orchestrated. Orchestrated by what, though not intelligence, no one was seriously suggesting that, but perhaps by structure. If the nucleus had internal stratification layers of different composition arranged in specific ways, then heating might trigger sequential releases. First, one layer vaporizes, then another, each at its own threshold temperature. The result would be a series of outbursts spaced irregularly but following a deterministic pattern set by the object's internal architecture. This is where self-organization becomes relevant. Complex systems, weather patterns, heartbeats, ecosystems can produce behavior that looks designed but arises from simple rules. The brain generates consciousness through billions of neurons firing in patterns that emerge from their connectivity. Maybe 3I Atlas, with its layered crust and stratified interior, was generating complex behavior through simple physics, heat flowing through materials of varying conductivity, pressure building and releasing in chambers shaped by eons of radiation damage. If true, then the heartbeat was not metaphorical. It was real, a rhythmic exchange of energy and matter driven by the comet's structure. The universe, acting through thermodynamics and chemistry, had built a kind of machine not conscious, not purposeful, but capable of producing outcomes that mimicked intention. Avi Loeb, when asked about the periodic variations, responded characteristically, "We should investigate all possibilities without prejudgment. If natural processes can produce regular patterns, we should understand how. And if they can't, we should admit that and look for alternatives." His position, controversial as always, was not that 3I Atlas was artificial. It was that science should remain open, willing to follow the data wherever it leads. The patterns, if real, deserved explanation. And if no natural explanation sufficed, then either our understanding of nature was incomplete or we were witnessing something genuinely new. Most of the scientific community sided with the incomplete understanding option. Nature is endlessly inventive. It has had 13.8 billion years to explore the space of possibilities. Somewhere in that vast space, there exist phenomena we haven't encountered yet, processes that will seem strange until we understand them, at which point they'll seem obvious. Three-Eye Atlas might be one such phenomenon. A comet whose structure and history produced behavior that doesn't fit our models, not because the models are wrong, but because they're incomplete, built from a sample of comets that doesn't include 12-billion-year-old interstellar wanderers. As the comet faded in November, the patterns faded with it. The periodic variations diminished, lost in the noise as the signal weakened. Whatever rhythms had existed at Perihelion, they were now beyond detection. The data was archived, the papers written, the debates tabled for lack of new information. But the questions remained, because pattern recognition is not just a cognitive bias, it's how science advances. Newton saw patterns in falling apples and orbiting moons. Kepler saw patterns in planetary positions. Darwin saw patterns in finch beaks. Every major discovery begins with someone noticing that things aren't quite random, that there's structure beneath the surface waiting to be decoded. Maybe Three-Eye Atlas's heartbeat was real. Maybe it was illusion. Either way, the fact that observers spent months arguing about it, analyzing it, trying to understand it, was itself significant. It meant that the comet had done something unexpected enough to push scientists out of their comfort zones, to make them question assumptions, to imagine possibilities they hadn't considered before. And in the end, that might be the comet's greatest gift, not answers, but questions. Because a universe that still holds surprises is a universe worth exploring. And a cosmos that can produce objects whose behavior borders on the inexplicable is a cosmos that will never stop teaching us humility. There are two conversations happening in science. The public one, conducted through press releases and peer-reviewed papers, is measured, cautious, hedged with qualifications. The private one, in emails and late-night conference calls and hallway exchanges, is where excitement lives, where speculation runs free, where scientists allow themselves to wonder. When Three-Eye Atlas exploded at Perihelion, the public conversation went like this: anomalous brightening behavior consistent with rapid sublimation of volatile ices. Further observations required to constrain models. Dry technical correct, but in the private channels the language was different. Did you see the timing? One researcher wrote to another. Within minutes of perihelion, how does ice know when to explode? It doesn't know, came the reply, but the precision bothers me too. This gap between public caution and private wonder is not dishonesty, it's prudence. Science has been burned before by premature announcements, by conclusions that later proved wrong. The cold fusion debacle of 1989, where claims of tabletop nuclear fusion turned out to be experimental error. The faster-than-light neutrinos of 2011, which were actually the result of a loose cable. The history of science is littered with exciting results that didn't survive scrutiny. So when faced with something genuinely strange, scientists retreat into careful language. They say anomalous instead of inexplicable. They say warrants further study instead of we have no idea. It's not cowardice, it's discipline, because the stakes are high. Say something wrong and you erode public trust. Overhype a result, and the backlash when it doesn't pan out damages the entire field. But there's a cost to this caution too. It creates a disconnect between the scientific community and everyone else. The public reads the press releases and thinks scientists are cold, unimaginative, allergic to mystery. They don't see the emails where researchers admit they're baffled. They don't hear the conference calls where someone says, "This is the strangest thing I've seen in 30 years." Carl Badams, after the Perihelion event, gave an interview to a science journalist. He was asked if he thought Three-Eye Atlas was unusual. His answer, carefully worded, "It exhibits characteristics that don't align with standard cometary models. We're working to understand the physics involved." Later off the record, he said something different. "It's as if you've been watching sparks for 20 years, and then one of them speaks." That second statement is the truth of the experience, the emotional reality of witnessing something unprecedented. But it's not the kind of thing you put in a paper. It's too poetic, too vulnerable, too open to misinterpretation. So it gets filtered out, lost in the translation from experience to publication. The pressure to maintain this filter comes from multiple directions. There's the peer review process where anonymity referees critique your work and recommend acceptance or rejection. Reviewers tend to be conservative, skeptical of bold claims. If you write that a comet did something impossible, you'll be asked to revise to cause unexpected. If you suggest that current models can't explain the data, you'll be asked to propose alternative models, even if you don't believe them. There's also the media. Journalists hungry for stories sometimes overstate findings. A paper saying, "Unusual spectral features warrant investigation," becomes a headline, "Scientists baffled by alien comet." The scientists then spend days issuing corrections, clarifying that no, they didn't say alien, and no, they're not baffled, just intrigued. After a few experiences like that, researchers learn to be even more cautious to use language, so hedged that it can't be sensationalized. And then there's funding. Research grants are competitive. Proposals need to promise clear deliverables, testable hypotheses, feasible timelines. If you write that you want to study a comet because it behaves inexplicably, you're unlikely to get funded.
But if you write that you want to test specific models of sublimation physics using a well-characterized object, the money flows. So scientists frame their curiosity in acceptable terms, translating mystery into methodology. Avi Loeb has been pushing back against this culture. After the anomalies of Oumuamua, its elongated shape, its unexpected acceleration, he argued that the scientific community should be willing to consider all explanations, including technological origin. Not because he believed it was alien, he clarified, but because excluding possibilities a priori is unscientific. The reaction was swift and harsh. Many astronomers accused him of sensationalism, of damaging the field's credibility, of giving fuel to conspiracy theorists. But others quietly agreed that the conversation had become too constrained, that there were ideas worth discussing that couldn't be discussed without risking one's reputation. When 3I Atlas arrived, Loeb saw an opportunity.
Here was another interstellar object exhibiting unexpected behavior. He called for full transparency. All observation data should be made publicly available immediately, not after the usual embargo periods. He argued that science advances fastest when information flows freely, when independent researchers can scrutinize data without gatekeepers. NASA and ESA responded that data does become public, but only after proper calibration and validation. Raw data can be misleading. Releasing it prematurely invites misinterpretation. The debate revealed a deeper tension: who owns scientific knowledge? The researchers who collect it, the institutions that fund the instruments, or the public whose tax dollars often pay for the research. In the case of 3I Atlas, most data did eventually reach the planetary data system and European archives freely accessible to anyone. But the delay, weeks to months, meant that by the time independent researchers could analyze it, the initial interpretations had already solidified. The first papers set the narrative, and later work tended to follow those frameworks rather than questioning them. This is how paradigms form. Not through conspiracy or suppression, but through the simple inertia of accepted ideas. Once a few respected researchers say, "It's probably just exotic sublimation physics," that becomes the working assumption. Proposals that challenge it have to overcome a higher burden of proof. Not impossibly high, but enough to discourage all but the most determined. What gets lost in this process is the sense of genuine mystery. The public often doesn't realize that scientists are uncertain, that many questions remain open, that the neat explanations in textbooks are sometimes just the best guesses available. When asked, researchers will admit this, but in formal communications they project confidence because that's what's expected. There's a parallel here with the ancient priesthoods, the intermediaries between common people and the divine. They spoke in formal languages, Latin, Sanskrit, that ordinary folks couldn't understand. They performed rituals whose meanings were opaque, and they held knowledge that was supposedly too sacred or complex for outsiders. Modern science isn't quite that, but there are echoes. The jargon, the peer review system, the conferences where researchers present to other researchers all create boundaries between experts and everyone else. It's not intentional exclusion, just the natural result of specialization, but it has consequences. When a layperson asks, "What was that blue comet?" and gets an answer full of sublimation rates and spectroscopic signatures, they leave feeling that science isn't for them. Some scientists are trying to bridge this gap. Communicators like Carl Sagan, Neil deGrasse Tyson, Brian Cox, they translate the excitement of discovery into accessible language, reminding people that science is not just equations, but wonder. When done well, this communication doesn't dumb down. It clarifies, revealing the beauty underneath the complexity. But it's hard work, and not all researchers are good at it or have time for it. And there's always the risk of oversimplification, of losing nuance in pursuit of clarity. The challenge is to convey both the knowledge and the uncertainty, to show that science is a process, not a collection of facts, and that mystery is not the enemy of science, but its driving force. Three-Eye Atlas, in its strangeness, offered a chance to practice this balance. Here was something genuinely puzzling, something that invited speculation while grounding it in data. In the months after, Perihelion astronomers gave talks to public audiences explaining what had been observed and what it might mean.
They acknowledged the uncertainties. They admitted they didn't have all the answers. And the response was not skepticism, but fascination. People wanted to hear about the mystery. They weren't looking for definitive conclusions. They wanted to be invited into the process of discovery, to feel what it's like to stand at the edge of the unknown. In those moments, the two conversations, public and private, converged. The careful language of papers gave way to the genuine excitement of researchers describing what they'd seen. And in that honesty and that willingness to say, "We don't fully understand this yet," there was a kind of grace. Because the universe doesn't owe us answers. It's under no obligation to be comprehensible. Every mystery we solve reveals deeper mysteries beneath. And if science is to remain a living endeavor, not just a catalog of known facts, but an ongoing exploration, it needs to preserve space for wonder, for questions that don't yet have answers, for phenomena that challenge our frameworks and force us to think anew. Three-Eye Atlas did that. It came from the deep past, flared briefly in our present, and left questions in its wake. And perhaps that's exactly what a messenger from another age should do, not provide easy answers, but remind us how much we still have to learn. There's a problem at the heart of planetary science, a puzzle that has vexed theorists for decades. It's called the meter-size barrier, and it goes like this. In a protoplanetary disk, dust grains collide and stick together, gradually growing larger. Micron-sized particles become millimeter-sized pebbles. Pebbles become centimeter-sized rocks. But when you reach about a meter in diameter, roughly the size of a boulder, something changes. At that scale, objects become vulnerable to aerodynamic drag. The disk is filled with gas, and as these meter-sized bodies orbit the star, they feel friction from that gas. This friction causes them to lose orbital energy and spiral inward toward the star. The time scale is short, thousands of years, maybe less, far too short for them to grow into planets through further collisions. So how do you get from meter-sized boulders to kilometer-sized planetesimals, the building blocks of planets? That's the barrier, and despite decades of research, no single mechanism fully solves it. Various ideas have been proposed: gravitational instabilities, turbulence, accretion streams, but each has problems, assumptions that don't quite work out when you run the detailed simulations. Susanne Pfalzner, an astrophysicist at Forschungszentrum Jülich in Germany, has proposed an intriguing solution. What if some planetary systems don't build their planets entirely from scratch? What if they capture interstellar objects,
Wanderers like 3i Atlas and use them as seeds. The idea is elegant. Interstellar objects are already large, often kilometers across, well beyond the meter-size barrier. If a young star system can gravitationally capture one of these visitors, as it drifts through the galaxy, that object becomes a ready-made nucleus. Dust and gas in the protoplanetary disk can then accrete onto it the way raindrops form around condensation nuclei in Earth's atmosphere. Within a few million years, the captured object could grow into a planetesimal or even a planetary core. The statistics support this. The galaxy is full of ejected debris from other systems. Every star that forms planets probably loses some in the chaotic early stages, flinging them into interstellar space. These wanderers then drift until they encounter another system. Falzner's calculations suggest that a typical protoplanetary disk might capture 1 or 2 interstellar objects over its lifetime. Not many, but enough to make a difference. If this process is common, it means that planets are not purely local creations. They're built from a mix of native material and imported matter, a blend of the home system's chemistry with fragments from elsewhere. Earth, by this reasoning, might contain atoms that originated around another star incorporated into our planet's structure billions of years ago. It's a kind of cosmic recycling. Stars are born, form planets, eject some. Those ejects wander, get captured by other stars, contribute to new planets. Over billions of years, matter circulates through the galaxy, mixing and remixing, never truly lost, always transformed. The Milky Way becomes an ecosystem, every part connected to every other, through the slow exchange of material. Now consider 3i Atlas. It's exactly the kind of object Falzner describes, large enough to avoid the meter-size barrier, rich in volatiles, that could contribute to a planet's water budget, old enough to have been available during the formation of countless star systems. It's a planetary seed, a potential building block that drifted for eons without finding a home. There's something tragic in that. This object carried within it the potential to become part of a world, to accrete mass, to differentiate into layers, to perhaps host oceans, atmospheres, even life. But it was never captured. It wandered for 12 billion years, always a visitor, never a resident. When it flared, at perihelion shedding gas and light, it was in a sense expressing that unrealized potential. The material it released, water organics, carbon compounds, was the kind of stuff that builds worlds. For a brief moment, it was contributing that material to our solar system, enriching the interplanetary medium with molecules from another creation. But it was too little, too late. The sun's planets had already formed, their composition set. 3i Atlas's offering drifted away, absorbed by the solar wind, dispersed into the vastness. Imagine, though, an alternate history. What if 3i Atlas had arrived 4.5 billion years ago when our solar system was still a disk of gas and dust? What if it had been captured, slowed by friction with the nebula, and remained? Its ices could have contributed to Earth's oceans. Its organics could have seeded prebiotic chemistry. Its rocky core, if it had one, could have become part of a planetesimal that eventually collided with the proto-Earth, adding mass and altering the planet's composition. In that timeline, we are made in part from 3i Atlas. Its atoms are in the ocean, in the atmosphere, in the cells of our bodies. When we look at the comet in 2025, we're not just observing a visitor, but recognizing a family member, a piece of our own origin story. This is not pure fantasy. We know that Earth accreted from many sources. Meteorites show that material from across the early solar system contributed to our planet. There's no reason to exclude interstellar contributions entirely. They're probably small. Most of Earth's mass is native to the Sun's protoplanetary disk. But even a fraction of a percent from elsewhere is significant. It means we're not purely solar, but galactic, made from ingredients that traveled light years to reach us. The philosophical implications ripple outward. If planets are built from a mix of local and imported material, then no star system is truly isolated. Every world is a mosaic, a blend of chemistries from multiple origins. The boundaries we draw, this is from our system, that is from elsewhere, are arbitrary. At the atomic level, there's only matter circulating through the cosmos, temporarily aggregating into stars and planets, and people then dispersing again when those structures decay. In this view, 3I Atlas is not a failed planet, but a participant in an ongoing cycle. It contributed material to whatever system it originated from. It may have passed through dozens of other systems over the eons, each time leaving a trace, adding its atoms to protoplanetary disks or planetary atmospheres. And now it has passed through ours briefly before moving on. In another billion years, it may encounter a young star system somewhere across the galaxy. There its timing might be right. It might be captured, slowed, incorporated. The material that once saw our sun would become part of that new world, carrying within it isotopic ratios that testify to a deep history, a journey that spanned ages. And on that world, billions of years hence, when intelligent beings emerge and begin to study their planet's composition, they might find anomalies, isotopic signatures that don't match their star's expected chemistry. They'll wonder where these atoms came from, how they arrived. And perhaps, if they're clever, they'll reconstruct the object's journey, tracing it back through the galaxy, back across time, back to a moment when it passed through a small yellow star in a distant spiral arm and was briefly observed by beings who called it 3I Atlas. In that sense, we are part of its story as it is part of ours. The observation was not one way. When we looked at the comet, we were also being seen, recorded in its isotopes and its memory, if matter can be said to remember. And when it moves on, it carries that memory with it encoded in the pattern of atoms, a message in chemistry that might one day be read by others. Suzanne Falsner has written about this with a poet's touch. These objects are not merely debris. They are envoys carrying the legacy of dead stars to newborn ones, ensuring that the galaxy's wealth, its matter, its chemistry, its history is never lost, but always recycled, always shared. 3R Atlas, then, was more than a comet. It was a seed that never sprouted a bridge between worlds, that never quite connected a message in a bottle that washed up on our shore, just long enough for us to glimpse its contents before the tide carried it away again. And in its passing, it taught us that the universe is not a collection of isolated systems, but a single interconnected whole, where every atom has a history that spans stars, and every world is built from the ruins and gifts of others. Science advances through the careful weighing of competing explanations. When confronted with a mystery, we propose hypotheses, test them against data, and see which survive. The process is messy, iterative, often frustrating. But it works. Over time, bad ideas are filtered out. Good ones refined, and understanding deepens. For 3I Atlas, 3 broad categories of explanation emerged in the months after Perihelion. Each had its champions, its strengths, and its weaknesses. Let's examine them in order of scientific support and plausibility. Hypothesis 1: Natural exotic chemistry. 60% likelihood. This is the mainstream view endorsed by most researchers who studied the object. The core idea: 3I Atlas behaves strangely because its composition and structure were unusual, shaped by 12 billion years of cosmic ray bombardment, but ultimately explicable through known physics. The mechanism combines several elements. First, the CO2 shield. The object's surface was coated in carbon dioxide frost, which sublimated gradually as the comet approached the sun. This layer acted as insulation, delaying the heating of deeper ices. When the last of the CO2 finally evaporated at perihelion, sunlight struck water ice, directly triggering explosive sublimation. Second, the irradiated crust. Cosmic rays had transformed the outer 50 feet of the nucleus into a dense, organic-rich shell. When this crust heated, it vaporized directly, producing carbon molecules C2 and nitrogen radicals NH2 without releasing dust. This explained the blue color and the absence of a tail. Third phase: transition. The interior likely contained amorphous ice, a glassy form of water that exists only at very low temperatures. When warmed past a critical threshold, amorphous ice crystallizes into ordinary ice, releasing heat in the process. This exothermic reaction provided additional energy, amplifying the eruption beyond what solar heating alone could produce. Together, these factors created a system poised on a knife's edge. The precise timing wasn't coincidence, but thermodynamics. The CO2 depleted exactly when the geometry and solar flux dictated it should. The violence of the eruption was a consequence of structure, billions of years of preparation culminating in a pressure release that happened quickly but inevitably. The evidence supporting this hypothesis is substantial. Computer simulations at NASA Goddard and the European Space Agency successfully reproduced the light curve when given appropriate initial conditions, a layered nucleus with specific ratios of CO2 to H2O, and irradiated crust with measured optical properties. The spectroscopy matched predictions for carbon-rich volatiles, photodissociating in sunlight. Even the energy budget, though tight, could be balanced if you included the latent heat from phase transitions. The main challenge is explaining the near-perfect symmetry of the outgassing. Random structural failures should produce asymmetric jets, causing the nucleus to tumble. Instead, the coma appeared uniform, suggesting simultaneous venting from multiple locations. The hypothesis addresses this by invoking uniform processing. If cosmic rays affected the entire crust equally, then thermal failure would occur globally, not locally. It's plausible if somewhat convenient. Roma Maggiolo summarizes the position: nature is complex. When you give it billions of years and extreme conditions, radiation, cold isolation, it creates structures we don't see in laboratories or in young comets from our own system. What looks impossible is simply unfamiliar. This is science at its best, taking what appears inexplicable and showing how it follows from established principles applied to unusual circumstances. No new physics, required just known physics in an unfamiliar regime. Hypothesis 2, rare, natural phenomena. 25% likelihood. The second category acknowledges that the first hypothesis, while plausible, leaves gaps. The timing is too precise, the symmetry too perfect, the energy budget too tight. Maybe there's something else going on, still natural, still within the bounds of physics, but invoking mechanisms less familiar, more speculative. One intriguing possibility: internal liquid water. If the object's interior contained radiogenic isotopes, elements like aluminum-26 or iron-60 incorporated during its formation, those isotopes would decay over time, releasing heat. This heat, trapped within the insulated nucleus, might maintain pockets of liquid water even in deep space. When the object neared the sun, thermal expansion could pressurize these pockets, leading to geyser-like eruptions. Earth's icy moons Europa and Enceladus provide precedent. They're heated by tidal forces, maintaining subsurface oceans despite being far from the sun. 3I Atlas wouldn't have tidal heating, but radiogenic heating is another route to the same outcome. If a subsurface ocean existed, even a small one, its sudden release at Perihelion would explain both the violence and the energy excess. Another idea involves magnetic fields. If 3I Atlas retained a remnant magnetic field from its formation, perhaps fossilized into metallic grains within the nucleus, that field could interact with the solar wind in complex ways. The interaction might create zones of compression and rarefaction in the surrounding gas, producing periodic oscillations, the heartbeat that some observers claim to detect. It's speculative but not impossible. Some asteroids carry weak magnetic fields. Why not an ancient interstellar object? A third mechanism is chemical clocking. Certain molecules, when frozen at extremely low temperatures, exist in metastable states. Configurations that are stable until disturbed, at which point they rapidly transform, releasing energy. Imagine a row of dominoes balanced precisely. Once the first falls, the rest follow in quick succession.
If the comet's interior contained such molecules, solar heating could trigger a cascade, a chain reaction that propagated through the nucleus faster than heat conduction alone would allow. This hypothesis category is where speculation begins to edge ahead of data. The ideas are grounded in real physics, liquid water, magnetic fields, metastable chemistry, all observed in other contexts. But applying them to 3I Atlas requires assumptions that can't be tested without a sample return mission, or at least much better observations than we obtained.
Suzanne Pfalzner, cautiously supportive of exploring these ideas, notes, "The universe has billions of years to invent phenomena we haven't thought of. Rare doesn't mean impossible. Every now and then conditions align in ways that produce something extraordinary. Our job is to remain imaginative while staying rigorous." The scientific community generally treats this category with interest, but not urgency. If better data emerged, if another interstellar object exhibited similar behavior and we could observe it more closely, these ideas would move from speculation to active investigation. Until then, their possibilities held in reserve. Hypothesis 3. Unknown. Mechanisms. 15%. Likelihood. Now we enter the most contentious territory. This category doesn't claim to know what 3I Atlas was. It simply argues that the natural explanations, while plausible, may be incomplete. Something about the object's behavior, the timing, the precision, the anomalies might point toward processes or structures we don't yet understand. To be absolutely clear, this is not a claim of alien technology. That specific hypothesis is perhaps 1% of this 15% mentioned here, only for completeness. The vast majority of unknown mechanism ideas involve natural phenomena that haven't been discovered yet. Consider precedent. When pulsars were first detected in 1967, their radio signals were so regular that astronomers half-jokingly labeled one LGM-1 little green men. It took months to confirm they were rotating neutron stars, a natural phenomenon that happened to produce clock-like pulses. The point is, nature can produce patterns so precise that they appear designed.
What might those unknown mechanisms be? Here are a few possibilities. All speculative new physics at macro scales, perhaps quantum effects normally confined to atomic scales, can manifest in specific materials under extreme conditions. If the irradiated crust created exotic quantum states, coherent matter waves entangled molecular clusters, their sudden disruption might release energy in organized ways. This sounds like science fiction, but physicists are still discovering emergent phenomena in condensed matter. It's not impossible that cold ancient matter could host surprises. Information encoded in matter. A more philosophical idea: what if matter itself carries information about its history in ways deeper than we recognize, not consciousness, but physical memory patterns in crystalline structure, isotopic distributions, magnetic domains that respond to environmental triggers? The perihelion eruption might have been, in this view, matter recognizing the sun's warmth after eons of cold, responding not randomly, but according to patterns embedded during its formation. This is highly speculative, bordering on metaphysical, but it captures a sense that some observers couldn't shake, that the comet's behavior felt responsive, not passive. Unknown. Astrophysical processes, perhaps interstellar space, harbors phenomena we haven't encountered because we've only observed 3 such objects. Maybe there are forms of radiation particle streams or field effects that accumulate over billions of years, creating structures or states of matter that don't exist in younger objects. 3I Atlas might be exhibiting the signature of processes that require deep time to manifest, processes our models haven't incorporated because we've never had reason to. And yes, for completeness, technological origin. Avi Loeb has argued that scientific rigor requires considering this possibility, not because it's likely, but because excluding it without investigation is unscientific. His reasoning: if intelligent civilizations exist, The Fermi paradox suggests they might, and if they've sent probes or created structures that drift through space, as we have with Voyager, then some fraction of interstellar objects might be technological. The prior probability is low, but not zero. Loeb's specific argument for 3I Atlas centered on the precision of the timing and the absence of expected debris. If you wanted to design a probe that maximizes visibility, he wrote, you'd time its brightest moment for perihelion when observers around a star are most likely to notice. You'd minimize dust to avoid erosion and maximize efficiency.
He estimated a 30 to 40% chance of non-natural origin, though he admitted that was a Bayesian prior based on his own assessment of the anomalies, not a calculation from first principles. The scientific community's response was swift and largely negative. Tom Statler, NASA's lead scientist for small bodies, said flatly, "It looks like a comet. It does comet things." The evidence overwhelmingly points to this object being natural. Most astronomers agreed. The anomalies, while real, were not so extreme that they required abandoning natural explanations. But Loeb's broader point stands: science should investigate the unexpected without prejudice. If we assume in advance that certain explanations are impossible, we risk missing discoveries. The history of science is full of examples where the consensus was wrong. Continental driftball lightning meteorites themselves, once dismissed as folklore because the evidence was dismissed before being examined. For 3I Atlas, the consensus is firmly with Hypothesis 1, perhaps, with elements of Hypothesis 2 to patch gaps. Hypothesis 3 remains at the margins, taken seriously by a small minority, treated with skepticism by most, but not entirely dismissed. And that's healthy. Science benefits from persistent skeptics and imaginative speculators as long as both remain tethered to data. The final verdict. We don't have one. The data are insufficient to conclusively rule in or out any of these hypotheses. What we have is a hierarchy of plausibility weighted by evidence and parsimony. The natural explanations are strongly favored, not because the alternative is impossible, but because it's unnecessary. Occam's razor don't multiply entities beyond necessity. If known physics can explain the observations, prefer that over invoking the unknown. But here's the subtle truth: known physics is always provisional.
What we know today is more than Newton knew, less than scientists a century hence will know. The universe continues to teach us, and every anomaly, whether ultimately explained by familiar principles or novel ones, is a gift, an invitation to refine our understanding. 3I to Atlas, in its strangeness, delivered such a gift. Whether it was a bizarre but natural comet, a harbinger of undiscovered phenomena, or something even stranger, it forced scientists to think carefully about their assumptions, to test their models against something truly alien. And in that testing, whether the models passed or failed, knowledge advanced. Perhaps that's the real lesson. The value of a mystery is not in its resolution, but in the journey toward understanding. The hypotheses we construct, the debates we have, the humility we learn when confronted with the unknown, these are the true gifts. And 3I Atlas, whatever it was, gave them generously. In the grand catalogue of cosmic events, the passage of 3I Atlas through our solar system will occupy a single line, a date, a designation, a few physical parameters. Thousands of years from now, if humanity still looks at the stars, archivists might note, third interstellar object detected, exhibited anomalous brightening at perihelion, origin unknown. But for those who witnessed it, the event meant more than data. It was a moment when the universe reminded us of its scale, its age, its strangeness. For a few months in 2025, people around the world looked up and knew that something impossibly old was passing through our neighborhood, carrying secrets from a time before time had meaning to us. The scientific legacy is still unfolding. 3I Atlas demonstrated that interstellar objects are not rare, not common either, but not so rare that we can ignore them. With better detection systems, we'll find more. The Vera Rubin Observatory, scheduled to begin operations in the late 2020s, will survey the entire southern sky every few nights, capturing faint, fast-moving objects that current telescopes miss. Estimates suggest it might detect 1 or 2 interstellar visitors per year. Each will teach us something. If they're all like 3i Atlas' strange, unexpected rule-breaking, then our models need revision. If they're diverse, each unique, then interstellar space is even richer than we thought, a zoo of phenomena waiting to be catalogued. And if some are mundane, well-behaved, that too is information. It tells us that 3i Atlas was an outlier, a rare case which raises the question, what made it different? These observations will feed into planetary formation models. Susanna Falsner's hypothesis that captured interstellar objects contribute to planet building will be testable. If we can measure the composition and structure of many such objects, we'll learn whether they're chemically compatible with being planetary seeds. If so, it reshapes our understanding of where planets come from, how solar systems acquire their material, and whether the boundaries between native and foreign matter are as clear as we once thought. There's also a practical dimension. If interstellar objects pass through the solar system regularly, could we intercept one sending a probe to match velocities with something moving at 37 kilometers per second is technically challenging, but not impossible. The European Space Agency and NASA have both sketched mission concepts. Project Lyra, for instance, that would use gravitational assists and advanced propulsion to chase down interstellar visitors. Such a mission wouldn't launch quickly. It would take decades to design, build, and fund. But the payoff would be enormous, a sample from another star system analyzed directly rather than inferred from spectroscopy. We'd finally know what lies beneath the irradiated crust. We'd measure isotopes with precision, mapping the original star's composition. We might even find organic molecules, complex chemistry, the building blocks of life, synthesized under alien conditions. That last possibility is not idle speculation. One of the driving questions in astrobiology is how universal is life's chemistry? Did life on Earth arise from ingredients unique to our world, or are the same processes happening elsewhere using the same molecules? Interstellar objects might carry the answer. If we find amino acids, nucleotides, lipid precursors in a comet from another star, it would suggest that prebiotic chemistry is universal, that the path from molecules to life is well trodden throughout the cosmos, and that would change everything. Because if the chemistry is universal, then life itself might be common, not intelligent life necessarily. Intelligence might be rare, but simple life microbes, ecosystems, the kind of biology that transforms planets. The galaxy could be teeming with it, invisible to our telescopes, but present, encoded in the rocks and ices drifting between stars. Beyond science, 3i Atlas had a cultural impact. For a few months, people paid attention to astronomy in a way they rarely do. Social media filled with images of the blue comet, with discussions of interstellar travel, with wonder at the idea that something 12 billion years old had touched our sky. Schools taught about it, podcasts discussed it, artists painted it. This matters because science thrives on public interest. When people care about the cosmos, they support funding for telescopes and missions. They encourage their children to study physics and astronomy. They vote for leaders who prioritize space exploration. The excitement around 3i Atlas brief, though, it was contributed to that cultural ecosystem, reminding a generation that the universe is not a static backdrop, but an active, unfolding story that we're privileged to witness. There's a personal dimension, too. For individuals who followed the story, 3i Atlas became a reference point, a memory tied to a specific time in their lives. Years from now, they'll recall where they were when they heard about the interstellar comet, what they felt when they saw the images. It will be a small memory, perhaps, but one connected to something vast, and that connection enriches us. Philosophically, 3i Atlas reinforced a truth that's easy to forget in daily life. We live in a cosmos far stranger and more wonderful than our routines suggest. The universe is old, vast, and full of surprises. We are small within it, but not insignificant, because we are the part of the universe that can look at itself and understand.
Every time we decode a light curve measure, a spectrum, propose a hypothesis, we're participating in the cosmos coming to know itself. That might sound grandiose, but it's not. It's simply the logical consequence of being conscious matter. The atoms in our brains were forged in stars, dispersed by supernovae, gathered by gravity into planets, assembled by evolution into thinking beings. When we study Three-Eye Atlas, we're not separate observers looking at an object. We're matter examining matter, the universe investigating a piece of its own history. And in that investigation, there's something sacred. Not religious necessarily, though it can be, but sacred in the older sense, set apart, worthy of reverence. To witness something that has endured for 12 billion years, to decode its message written in light and chemistry, to imagine its journey through the dark, this is as close to transcendence as empiricism allows.
The legacy of Three-Eye Atlas, then, is not just what it taught us about comets, or interstellar objects, or planetary formation. It's the reminder that we live in a universe that still holds mysteries, that refuses to be fully known, that constantly presents us with phenomena that challenge our understanding and invite us to grow. In a century, humanity might have a complete theory of interstellar objects, a taxonomy that explains every visitor, a set of models that predicts their behavior with precision. Or we might still be puzzled, still arguing about edge cases, still surprised by outliers. Either outcome is fine. What matters is that we keep looking, keep questioning, keep allowing ourselves to be amazed. Because the universe is patient. It's been here for 13.8 billion years, and it will be here long after we're gone. It doesn't need us to understand it, but it offers itself to us anyway through light and gravity and chemistry, through comets that cross the void and stars that burn in the night. And our response, this endless, curious, fumbling attempt to understand, is our way of saying, thank you. Three-Eye Atlas is gone now, a fading speck in the telescope archives, a set of numbers in the databases, but it left something behind, a story, and as long as someone remembers that story, as long as anyone looks up at the night sky and wonders what else might be passing unseen, the comet's journey continues, not through space, but through us. Let's gather what we know, what we don't, and what it means to stand in that space between. We know that Three-Eye Atlas is real. Third confirmed interstellar object, detected July 2025 Perihelion. October 29th at 1.36 astronomical units from the Sun, hyperbolic orbit eccentricity 6.137, velocity 37 kilometers per second, age estimated between 7 and 12 billion years. These are facts measured and verified. We know it exhibited extraordinary behavior. Brightening increased 40-fold in hours centered on perihelion. Spectrum shifted to blue, dominated by carbon and nitrogen emissions. Water vapor production reached 5.7 times 10 to the 28th molecules per second, 40 times theoretical predictions. No dust tail formed. The timing was precise, the symmetry remarkable. We know its surface was transformed by cosmic rays, 50 to 65 feet of irradiated crust, carbon-rich organics synthesized over eons. Beneath that shell, likely pristine ices from its formation. The crust acted as insulation until solar heating breached it, triggering explosive sublimation. These are the certainties, the foundations on which all interpretations rest, but they're dwarfed by what we don't know. We don't know exactly what triggered the eruption. The CO2 shield hypothesis is compelling but not proven. The phase transition idea adds plausibility but remains speculative. The energy budget balances only if you make assumptions about internal structure that can't be verified. We don't know why the outgassing was so symmetric. Random failures should produce asymmetric jets. The uniform appearance suggests simultaneous venting across the entire surface, but the mechanism for that synchronization is unclear. We don't know what lies in the interior.
The pristine core might hold isotopic ratios revealing the object's birth star or prebiotic molecules, or exotic chemistry we've never encountered. We'll probably never know. The object is receding already beyond reach. We don't know if the periodic variations were real or artifact. If real, we don't know what caused them: rotation, internal oscillations, magnetic effects. The data quality was marginal, the interpretations contested. We don't know if other interstellar objects will behave similarly.
Maybe 3I Atlas was typical, and our models need revision. Maybe it was unique, a rare combination of age and composition that won't repeat for centuries. Only time and more observations will tell, and most fundamentally, we don't know if we're asking the right questions. Every mystery solved reveals deeper mysteries. The more we learn about 3I Atlas, the more we realize how much we don't understand about comets, interstellar space, deep time, the processes that shape matter over billions of years. This uncertainty is not a failure. It's the nature of science. We build models, test them, find they're incomplete, refine them, repeat. The process is endless because the universe is inexhaustible. There will always be phenomena at the edge of our understanding, always cases that don't fit neatly into categories, always surprises. And that's good, because a universe fully understood would be a universe fully dead, drained of wonder, reduced to calculation. The gaps in our knowledge are where discovery lives, where curiosity thrives, where the next generation finds its purpose. So where does that leave us with 3I Atlas, with a story incomplete, a mystery unresolved, a question mark hanging in the sky? And that's exactly right, because the comet's gift was not answers, but questions, not closure, but opening, not certainty, but the invitation to wonder. If you're listening to this now, perhaps in the quiet hours before sleep, consider this: somewhere out there, beyond the reach of our instruments, 3I Atlas is still moving. It's crossing the heliopause, passing through the termination shock, entering the interstellar medium once more. The sun's warmth, which briefly woke it, is fading. Its surface is refreezing the crust, sealing again the interior, returning to cold dormancy. In 1,000 years, it will be light days away. In 1,000,000 light years. In 1,000,000,000, it might encounter another star, another moment of warmth, another chance to flare and be seen. Or it might drift forever, silent, untouched, carrying within its frozen heart the memory of 2 suns, its birth star long dead, and ours briefly glimpsed. We will not see it again, but in a very real sense, it saw us. The molecules it shed at Perihelion contained information chemical signatures, encoding our sun's spectrum, the solar wind's composition, the radiation environment of our inner solar system. If anyone ever samples that material, unlikely, but not impossible, they'll be able to reconstruct this moment, our star, our time. And perhaps in that distant future, other observers will look at the data and wonder who might have seen this object when it passed through, whether anyone noticed, whether anyone cared. And the answer echoing across the eons will be yes. We saw, we cared, we wondered.
As you drift towards sleep tonight, carry this thought. The universe is old beyond comprehension, vast beyond imagination, strange beyond prediction. But it is not cold, or hostile, or indifferent. It's filled with messengers like 3I Atlas, carrying stories, inviting questions, reminding us that we're part of something immeasurably larger than ourselves. We are stardust, looking at starlight, contemplating stardust. We are the universe, examining itself through temporary arrangements of matter that happen to be conscious. And for a brief moment, cosmically brief, humanly eternal, we witnessed an ancient traveler pass through our neighborhood, and we were changed by it. Not because we understood it completely, we didn't, but because we tried, because we looked up, because we asked why and how and what does it mean, because we refused to let mystery be the end of the conversation and made it instead the beginning.
So here is the final question, the one that lingers after the data is archived and the papers published and the telescope time reassigned. as Three-Eye Atlas crosses the heliopause and returns to the interstellar dark, carrying with it the brief warmth of our sun's light, we're left to wonder, in the 12 billion years before it reached us, and in the billions of years ahead as it wanders onward, will it encounter other suns, other worlds, other eyes looking up in wonder, and more unsettling still of all the interstellar visitors that pass through our cosmic neighborhood, in silence and darkness never see, never known how many carry stories. Even stranger than this one, what messages are sailing past us right now, just beyond the reach of our instruments, waiting for the day when we finally learn to see them. Sleep now with the knowledge that the cosmos is vaster and stranger than any dream. And when you wake, the stars will still be there waiting, watching, wandering.
Good night, fellow travelers.